Dear ladies and gentlemen, I'm very happy to welcome you to this highlight event this evening. My name is Klaus Lemmerzahl. I'm professor for theoretical physics at the University of Bremen and also at the University of Oldenburg, and I'm director of the Space Science Department at SARM. My special research area is gravitational physics, and this includes theory, experiments, and modeling. Now to the talk. Let us imagine that we could not hear, that we are completely deaf. How terrible that would be. Put on the microphone again, thank you. So you have understood what I meant. This was just a demonstration. The acoustics is okay here. So what I did say was, a lot of important information would not be available to us. We could not listen to music, we could not listen to the news, and lectures and a conference like this would not be possible. You could not enjoy the sound of waterfalls, the chirping of birds, and we would not hear the sound of thunders and explosions. That is it. When we look up to the sky, we can only see. Of course, we can see a lot, and what we see is, of course, very exciting and interesting. We see stars, galaxies, jets, nebula, very beautiful things, but we hear nothing. We lack important information about the events in the heaven. And today, we have Professor Carsten Danzmann with us, who has enabled us to hear these processes in the universe. He is making it possible for us to measure, to hear gravitational waves. This, in turn, is made possible by the fact that in the recent decades, he and his group have developed new groundbreaking technologies in the field of quantum optics. With this, for 3 years, we are now being able to measure gravitational waves and to receive completely different information from the events in the universe than is available to us by just seeing. The technology developed by Carsten Danzmann is, however, not only used for the exploration of the distant events in the universe, but also for very practical purposes, for geodesy, for geophysics, for climate research, and much more. That is, for things that clearly serve the benefit of mankind. Professor Carsten Danzmann is director of the Max Planck Institute for Gravitational Physics, also known as the Max Planck Institute, and director of the Institute for Gravitational Physics at the Leibniz University of Hanover. He studied physics in Clausthal-Zellerfeld and made the diploma as well as his PhD at the University of Hanover. After his PhD, he had research stays in Stanford and at the Physikalisch-Technische Bundesanstalt in Braunschweig. In the early 90s, he became the project leader for the gravitational wave interferometer GU600, built up near to Hanover, which was completed in 2005, and he also proposed a space mission called LISA, Laser Interferometer Space Antenna, and I think we will hear a lot of that later on. Professor Danzmann has been awarded many very prestigious prizes, among others the Max Planck Research Prize, the Körber European Science Prize, the Otto Hahn Prize, and the Stern-Gerlach Medal of the German Physical Society. He's also speaker of various graduate schools, indicating his great interest in the education of young people, which also is a very important topic of this conference. And now, Carsten, please come to stage and teach us the sound of gravity with your talk, Gravitational Wave Detection on Ground and in Space. Thank you very much for coming.
Ladies and gentlemen, astronomy is no longer what it used to be. I'm here today to tell you a story. Our story. Our story made 671 cover pages of magazines and journals all over the world. Journals like this one here, daily newspapers like this one here, and we've also managed to make it on the cover page of the most important science publication in all of Germany. This one here. Of course, what was really important on the day is in big print here. But look here on the right, there. There we are. I had never thought we would someday make it on the cover page of the Bild-Zeitung. When that happens, you know you've made it in life. What had happened? We had detected gravitational waves. And we also made the cover page of this journal, Physical Review Letters. For a physicist, maybe almost as important as the Bild-Zeitung. This was the result of a grand undertaking over many decades of many, many people. The paper in Physical Review Letters had 1,004 authors, as you can easily count on this complete author list here. And they came from 133 institutions in the world. A truly grand undertaking. And finally, it was awarded the Nobel Prize in Physics for these three pioneers of the early days of gravitational wave research. But let's take it slowly. What are gravitational waves? Gravitational waves are plane, quadrupolar, transverse distortions of space and time. I will test that later on, so please remember. Quadrupolar, transverse, planar waves. As you can see here, of distortions of space and time, you see that the wave is traveling backwards in space, and space is distorted horizontally, vertically, horizontally, vertically. And this already tells you what the best way is to detect gravitational waves. If space is stretched and squeezed, then distances will change. So all you have to do to detect gravitational waves is measure length changes. And the best instruments to measure length changes are laser interferometers. Unfortunately, the laser interferometers weren't good enough for about 100 years. That's why it took so long, because it's now over 100 years ago that Einstein predicted gravitational waves as a consequence of his theory of general relativity. But nowadays, there are several kilometer-sized big observatories listening out into space. The two LIGOs in the US, Virgo in Italy, our own GEO 600 near Hanover. Our Japanese colleagues are constructing an underground interferometer of 3-kilometer arm length. And just a year ago, the Indian government has given permission to start construction of LIGO India. And all of these instruments have been observing around the clock for 2 years until the year 2011. With a sensitivity which was not too bad. What is plotted here is the relative squeezing of space. And you see it's a few times 10 to the minus 23 that space is stretched and squeezed over the frequency of a few hertz up to about a kilohertz. Not so bad, but unfortunately, the universe is empty, particularly around us. And you can calculate that with this sensitivity, the expected event rate is at best once per year, at worst, maybe once per millennium. And the interferometers have observed for 2 years around the clock and have not detected anything. So the prediction was correct. But it was always the plan to go into upgrades. And this upgrading to advanced LIGO took 5 years. And it took place from 2011 until 2015. It was a major upgrade. Literally everything was gutted. Almost nothing remained except the buildings and the big vacuum tubes. And we're very proud that many of the things that went into advanced LIGO to make it more sensitive came from us. The mirror suspensions, the new optics, the high power lasers, and the complete signal enhancing optical layout. And then after 5 years, a process known as commissioning started. Commissioning is a very innocent word for this process. When you start operating an interferometer, what do you detect? Noise. The whole life of a laser interferometrist consists of studying noise. And then you find out why it is noisy, remove the noise source, turn it back on, and it's noisy. If you're lucky, a little less noisy. And here you can see how the sensitivity of advanced LIGO improves over 8 months from June 2014 to February 2015 by a factor of 200. This is a logarithmic scale. 200, these are the glorious days in the beginning of the commissioning, when every day you gain a factor of 2, and then it gets tedier and tedier. And by September of 2015, advanced LIGO was already a factor of 10 better than initial LIGO, but still a factor of 3 away from the design sensitivity. Nevertheless, that's the time when you say, okay, let's run it for a while. Let's take some test data, see how it behaves. That beginning of data taking was planned for October 2015. And then came September 14 of 2015, the day that should change the lives of these 2 postdocs in our institute profoundly. It was a Monday. It was a Monday morning at 11:50 at the AEI in Hanover. A beautiful Monday, like always in Hanover. LIGO was still in commissioning. It was still being turned and tweaked. No data taking was really planned. As a matter of fact, this was the first day after 5 years of commissioning, of building, that the detectors were reasonably behaving. Our postdocs were doing what they always do on a beautiful Monday morning at 11:50. They were staring at their computer screens. And then it happened. It went beep or toot. An alert came along, or to be more precise, the Coherent Wave Burst Data Analysis Online pipeline had sent an alert to Marco Drago, to his computer. Whenever the detectors are taking data, there are several computer pipelines watching the output, trying to detect when something unusual happens. And when the same unusual thing happens in the other detector, within plus minus 10 milliseconds, an alert is generated. That's nothing unusual. It happens several times a day. And actually at that time, there were about 1,000 of these alerts in the pipeline to be looked at. And a human then has to look at these and say, oh yeah, what was it? So did a bag of rice fall over, or did a car crash into the building? It's usually something mundane like that. And so Marco thought, well, let's see. He looked at the database. There was nothing unusual in there, strange. So he called his friend Andy from across the hall. Andy, look at this, there's nothing unusual. But Andy said, why don't you look at the data itself? Good idea. And then they saw the signal, and they couldn't believe it. You know why? It was too beautiful. Too beautiful. It looked like a human had created it and inserted it into the data stream. That wouldn't be unusual, because we do this all the time during commissioning to test the data analysis pipeline. You wiggle a little bit the mirrors, and then you look at the end of the data stream whether the correct signal comes out. So they looked again at the database, because there must be an entry, test signal. Nothing. They were very confused. Then they called up the control room. But it was 2 o'clock in the morning and 5 o'clock in the morning in Louisiana and in Washington State, and there was only the night watch telling them, what do you mean test signal? We're all sleeping. They've all gone home here. By that time, half our institute was standing in their offices looking at that, and an hour later they sent an email to the whole 1,000-member collaboration. Was this a test signal? And if yes, why didn't you tell us? Why do we have to get so upset here? But it wasn't. The next few hours saw literally hectic activity. Thousands of emails went back and forth across the Atlantic. And after 12 hours, the decision fell, freeze the detector state, hands off, we have to look at this more closely. This could be real. And now, what was it that got them so excited? It was this. This is the actual signal. It was so big, you could see it without data analysis in the raw data with your naked eyes. This was the first time humans were listening to black holes dying. And this is what they were listening to. You can hear how they get closer and closer and closer. Then they touch, and with a little plop, they're gone. You could not imagine how many times this signal was imitated in the following weeks in our institute by humans with their mouth. Wit! Make me a black hole, yeah. But now I admit this was a simulation. We were training your ear, because now we're listening to the real signal. And the real signal is noisy, of course, because it is sitting on the background of detector noise. So you will see the real signal here in Hanford and Livingston and 2 detectors in the upper panel as a time frequency diagram. So you will see it coming in at about 30 hertz, chirping up to 250 hertz. You will also see the time domain waveform at the bottom, and you will hear it. You will hear it 4 times. First in the original pitch, then upshifted by 400 hertz to make it more audible. Then again, the original pitch, where the maximum is at 100 hertz only, and then upshifted again. And this is what it sounds like when black holes die. Isn't this beautiful? I've worked for 28 years to hear this. Wasn't it really worth it? There's a lot of information in these waveforms. From these waveforms, you can tell that the original objects were 2 black holes of 36 and 29 solar masses. You can also tell that the final object was a black hole with 62 solar masses. And if you add the first 2 numbers and subtract this from the third number, then you will see there are 3 masses missing. 3 solar masses. Within a tenth of a second, 3 solar masses were burnt in this event and converted into pure radiation, into gravitational radiation. For a fraction of a second, this event was 50 times as luminous as the whole rest of the universe combined. You can also tell how far away it was. There's the luminosity distance there, 410 megaparsec. 410 megaparsec, that's roughly 1.3 billion light years. That's pretty far away, you might think. It's also pretty long ago. It means the signal was created 1.3 billion years ago. So 1.3 billion years ago, way out there, 2 black holes merged, and the signal traveled and traveled and traveled until it reached us here on the Earth 1.3 billion years later, on the very day that after 5 years of complete reconstruction, both detectors for the very first time were stably running with a decent sensitivity. Sometimes you just got to be lucky in life. So that's what happened. There are the 2 black holes circling each other. You see the 2 black hole horizons. This is a simulation of what you would have seen out there. But gravitational waves were also created, and this is not a simulation. This is a complete numerical solution of Einstein's field equations that runs about 3 weeks on our supercomputer cluster. You see the 2 black holes in the center in black. To scale, that's how big they are, that's how far away they are. You see them circling in. You see the gravitational wave as space-time curvature going out. Now you see how they get closer and closer. And in a second, they will touch. Then you see a blip. Then it rings a little bit. And then it is quiet. It's all gone. It has to be quiet. Because there's a law that says black holes do not have hair. I know that happens also to humans, but this means something else. It means that black holes don't have properties except for mass and angular momentum. The black hole that was created after the merger was excited. It didn't want to be excited, and so it radiated away its excitation energy quickly. Or for the mechanical experts among you, black holes are highly damped. They have a mechanical Q on the order of a few dozen. That's about the viscosity of jello pudding. Götterspeise auf Deutsch. So if you want to make yourself a picture of a black hole, cook yourself black jello pudding, schwarze Götterspeise, hit it with a spoon, not too much, so, and then the jello pudding will go, brrr. That's black holes. That's how they behave. Now, you probably want to know where it was on the sky. Well, we asked the same signal. Unfortunately, we couldn't really pinpoint it too well the first time. Here you see a map of the sky, Sirius, Orion, the Small Magellanic Cloud, and there is a crescent-shaped area on the sky that had a size of 600 square degrees. With only 2 detectors, we couldn't localize it to better than 600 square degrees. Nevertheless, there were 20 follow-up campaigns with all kinds of optical telescopes in the radio, optical, IR, X-ray, gamma ray. And what did they detect? Nothing. The event was absolutely dark. This was the most luminous event ever detected by mankind, and it was dark. It consisted of nothing else but space-time curvature. This was the first time that we got a signal from the dark shadow world that is out there. And we know that more than 99% of the universe is dark and will never be observable with any type of electromagnetic radiation. But everything interacts via gravity. And everything that interacts via gravity and forms structure must radiate gravitational waves. By now, this is routine. When the detectors are running, we are now detecting black hole mergers every month. More black holes have now been discovered with gravitational wave detectors than ever before indirectly suspected from X-ray observations. And all our black holes are much, much heavier than the ones that were hypothesized before. This has given rise to an intriguing speculation. If this holds up, then we have so many black holes that they actually could be dark matter and solve a problem that has been with us for decades. There are processes that could create these black holes in the primordial times in the early universe. And now we see them merge. The verdict is still out. About every week there is a paper on the archive, and every author says that what the others are saying is total nonsense. I would say we have a 50% chance that black holes are at least an appreciable fraction of the dark matter in the universe. Okay, people were getting bored and said, oh, again a black hole. Can't you detect something else? Well, we did. On August 17th, for the first time, we saw the merger of two neutron stars. Neutron stars are tiny little objects, 10 kilometers, but the mass of a sun, pure neutron matter, and we saw them merge. And this time, it didn't take a tenth of a second. We could listen to the death dance for 100 seconds while they were circling and circling and circling each other. And then finally they merged. There's the merger signal, and 1.7 seconds later, two gamma ray detectors detected a gamma ray burst. Now, gamma ray bursts have been among the most mysterious objects, signals with us again for decades. It has always been suspected that the merger of neutron stars might be the source for gamma ray bursts. Now we know, but even better than that, because we could localize the event on the sky with gravitational waves much better than the gamma ray detectors that gave the optical astronomers a chance to find it. And 11 hours later, the 1-meter telescope in Las Campanas in South America found it. They found the galaxy. There on the right, you see it 20 days before. And up there, they found it 10.9 hours after the merger. And you see, there's a new star there. That was our neutron star merger. This was followed by the biggest follow-up campaigns ever in optical astronomy. 70 telescopes all over the world followed this in the radio, X-ray, gamma ray. They saw the signal. It was the very first time that we could see the emergence of a cosmic fireball that was baking heavy elements. You can see them with spectroscopy. So far, we had no idea where all the gold in the world was coming from. All the elements heavier than iron are a mystery to us, and now we've seen it. The gold that you're wearing on your finger, that you're wearing around your neck, was probably baked 6 billion years ago in the merger of two neutron stars here, was then blown out into the universe, later assembled, merged, forming the Earth. And 6 billion years later, we dig it out of the ground and wear it. Now we know. Einstein, by the way, never thought that gravitational waves would ever be detected. As a matter of fact, he changed his mind 5 times in his life, whether gravitational waves do even exist, or whether they were mathematical artifacts of his theory. But I think he wouldn't mind that he was wrong.
Good job.
There's one thing that you probably don't know, and that is that German researchers have been among the pioneers of experimental gravitational wave research since about half a century. Already in a time when there were no laser interferometers, when people were using resonant mass detectors like this one here, it was a German group that was chasing them. Here you see Heinz Billing looking at his bar detector. Later, I was his successor in the Max Planck Society. That was 28 years ago. And when I took over his job, he told me, Herr Dunzmann, I will tell you one thing. I will stay alive till you have detected these gravitational waves. Well, he managed. So we could tell him that we had detected them, but I think he had no idea that he had to become 102 years old before it became true. Anyway, then came the laser interferometers. It was again this group that built probably the first true prototype of a laser interferometric gravitational wave detector. Laser interferometers. What do you need? Two things, right? Interferometers, lasers. The interferometers we had in Germany, in Bavaria, this is a historical picture of the 30-meter interferometer of the Max Planck Society in Garching, near Munich. But the lasers also existed up north in Hanover. And this again is a historical picture. I love this picture. This is a CW 720-watt neodymium YAG laser built in 1974. So when I was a student, I did see this before it was scrapped. Beautiful digital instruments up there and the polyethylene tubing for the cooling water that always popped off and flooded the whole basement. But the thing was working. This is the great-grandfather of all lasers that are now operating in all gravitational wave detectors in the world. They all came from Hanover. And the interesting thing is, this thing was not built for gravitational waves. It was not even built to measure anything. It was built for surgery. It was built because colleague Pichelmeier complained with colleague Welling that it was always bleeding like hell when he cut into a liver with his scalpel. And he said, Herbert, do something to coagulate immediately so I can see something, and Herbert did. Here you see a beautiful clean liver cut on the right, immediately coagulated, no blood. It worked so well you can operate on living pigs with that. Okay, now you can open your eyes again, the blood is gone. This all came together then later at the AAI in Hanover. For many years I was alone, then we added data analysis, then 3 years ago we added the waveform generation, and nowadays we're operating the worldwide largest dedicated computer cluster for the gravitational wave data analysis. All data from all detectors in the world is sitting in our basement, looking for tiny little things like that. We are also operating our own laser interferometer called GEO600, which is small but nice and very inexpensive, because we had built it with our own hands. Our students and postdocs were coming in with shovels and wrenches and soldering irons, building a gravitational wave detector. Some people say it was built with slave labor, but I tend to say we give young people the chance to early on work at the forefront of international science. What came out of it was GEO600, a German-British collaboration built on the grounds of the Institut für Obstbau und Baumschule. That's the Department for Agriculture of the Leibniz-Universität Hannover. Here you see it, built. It's not really a gravitational wave detector. It is a think tank. It's a technology pioneer where we always try out and develop the technologies for the next generation of interferometers. Advanced LIGO is, of course, much bigger, much nicer, but also much more expensive. $1.3 billion have been spent so far to make these detections possible. Now, you might calculate, right? You remember how far away was the source? 1.3 billion light years. So now we have a scaling law, right? It's about $1 per light year distance. But this money did not go into sensitivity. Most of it goes into digging dirt, building buildings, roads, stainless steel. What makes the sensitivity is the little stuff inside. Diodes, detectors, mirrors. And there we are very happy that all the advanced technologies that we developed made their way into advanced LIGO, making it so much more sensitive than initial LIGO. The signal recycling, the signal enhancement technology has been running on GEO600 for about a decade already. The high power lasers were built in Hanover, installed by us on the site, and the monolithic fused silica mirror suspensions have been running on GEO600 for over 7 years around the clock now. So we see a flourishing gravitational wave astronomy coming up on the ground. And we are already on the drawing board for the third generation to go into operation in 15 years, maybe. The best known design concept is known as the Einstein Gravitational Telescope, or in short, also sometimes known as ET, which will be an underground interferometer, 30-kilometer beam tubes, cryogenic, non-classical light, everything we can think of that makes an interferometer more sensitive. But what ET cannot do is look at the low frequency signals. From the ground, we will probably forever only be able to detect in the audio band. That's frequencies from a few hertz to a few kilohertz. Frequencies that our ears could hear if they were about a billion times more sensitive, because then even our inner ear would be stretched and squeezed by gravitational waves. If you want to detect the low frequencies, you have to go into space. You have to build LISA, the Laser Interferometer Space Antenna, and that will open the low-frequency gravitational universe, consisting of 3 satellites at the corners of an equilateral triangle with million-kilometer arms. Not kilometers like on the ground, million kilometers in a heliocentric orbit, roughly 50 million kilometers behind the Earth. And with such a detector, we will not detect the collisions of little black holes. We will detect the collisions of whole galaxies. And when that happens, then the supermassive black holes that are in the centers of these galaxies with millions to billions of solar masses, they will get so close that they emerge in a gigantic flash of energy, only comparable to the Big Bang itself. Here is an example, the galaxy NGC 6240, and if you home in with the Chandra X-ray telescope, then you see 2 bright blobs in there. These are 2 black holes that are about to merge with each other in only 80 million years. So we put the satellites there, and if we do it right, then the triangle is in a purely passive orbit around the sun, and it looks like it would be orbiting the sun like a rigid body, like a cartwheel rolling around its center once per year, when in reality, each of these satellites is in their own heliocentric orbit. But the 3 orbits are slightly elliptic, slightly inclined against the ecliptic, and the ascending nodes displaced by 120 degrees around the ecliptic. And that makes it orbiting like a rigid body in there. Now, if you do something complicated like this, you want to be certain that it works. And for that, you need a demonstrator, a technology demonstrator. And this mission is known as LISA Pathfinder. Finding the paths for LISA in space. The idea behind LISA Pathfinder is straightforward. Take one LISA arm, a few million kilometers long. What's at the end of the arms? Gold. 2 free-floating gold cubes about the size of my fist that are following purely geodesic orbits, freely floating inside the satellite, because that's what we want to measure. The distance change between them due to gravity, due to the distortion of space-time. But it's a bit inconvenient. So you take the LISA arm and shrink it down to 38 centimeters. And then it fits into one satellite. And there it is. And then you build a little laser interferometer in between, and you can test pretty much everything you need for LISA except the long arm. There it is. It took only 18 years from the day when I wrote the first proposal for LISA Pathfinder till the satellite was ready. There it is in September 2015. What a month that was. A few weeks earlier, we had detected gravitational waves for the first time on the ground. We knew, but nobody else knew, because it was another 5 months before we told anybody. And then this happened. We launched LISA Pathfinder on December 2nd of 2015, and if you look in the history books, this was exactly to the day 100 years after the publication of Einstein's general relativity in written form. No PR agency could have done that any better to celebrate 100 years of GR, but it was purely accidental. It only happened because we had a 1-week launch delay, and that put us smack on this day. And then it happened. Kourou, French Guiana, at 1 a.m. I'm sure you've seen plenty of these launch videos.
8, 7,
But this is
6,
impressive. A night
5,
launch at 1 a.m.
4,
in Kourou. You're
3,
standing there,
2,
40 degrees, 100% humidity, 100% mosquito saturation, and you see your rocket in the far distance launch. Then it comes over your head, and when it comes over your head, the roar from the takeoff also arrives. It's a really captivating moment. It was shortly after an operation at the Lagrange point 1.5 million kilometers from here towards the sun. This was the first laser interferometry in space ever. It was also the first distance measurement between free-flying test masses in space ever. There they are, 2 gold cubes flying freely in space. All the rest is just diagnostics and measuring stuff. And we again made the cover page of Physical Review letters. Because what had we done? We had created the stillest place in the universe. The test masses were so quiet and the interferometry was so sensitive that it would have been a big signal if a virus, not a bacterium, they are large, a virus had sat down on one of the proof masses with its weight. Chunk. Or to be a little more quantitative, this is the residual acceleration spectrum that we measured on the mission. There you see an hour, a minute, and a second time scale. And the blue bar is 1 femto-g. That is 15 orders of magnitude less than the acceleration of gravity in this lecture hall. Now that was our requirement. And you see the full LISA requirement, and you see the LISA Pathfinder requirement. Traditionally, precursor requirements are relaxed by about a factor of 10, and that's what you see here also. And then it happened, March 1st, the first day of operations when we scientists took control over the satellite. Everything non-optimized, straight out of the box, as industry had built it. We just turned it on by dead reckoning, and that's the first spectrum that we got, way below the LISA Pathfinder requirements. We could have gone home. Everything was fulfilled. But physicists don't go home. They get greedy. We started optimizing, understanding the mission. 2 months later, this is where we were. We had for the first time reached the requirements for the full mission. But even more important was that we understood why. Because here you see the various noise sources. I do not want to dwell on this. There are things like phase meter sensing, actuation noise, stray voltage fluctuations, laser radiation pressure. But over the most part, you see there up there gas damping. That's the residual momentum impact due to the few remaining gas molecules inside the good vacuum. But we opened the system to space 62 days after launch, and then it started outgassing, and you can see the low frequency noise fall and fall and fall as a perfect 1/T, like a perfect vacuum system, and that's the final curve. That's the sensitivity we got, and we're about a factor of 3 below the requirements for residual force noise for the full mission. If there's any way to summarize the results of LISA Pathfinder, LISA works. All you have to do is get $1 billion or $2 billion and start building. ESA, thank you. ESA has reacted. They were anticipating your applause and has anticipated the selection cycle for the next large mission by 4 years. So the call for mission concepts came out in 2016. NASA was back in the game with a few $100 million. We submitted a mission concept document, which is still on the web. It's a beautiful document. Not only does it have beautiful colors on the cover, but it also has 42 pages. And as you might know, 42 is the answer. That's what we are proposing. 3 arms of 2.5 million kilometers, 2-watt lasers, 30-centimeter telescopes that makes the constellation breathe by about 1 degree per year. That makes the satellites move so that the Doppler shift of the laser beams is about plus minus 5 megahertz. That, by the way, is good for us. A ground-based interferometer is dark at the output. It's sitting on a dark fringe. A space-based interferometer has the fringes running through at 5 megahertz. But that's for us very good because it means the interferometer self-calibrates 5 million times a second. Every time a fringe runs through, you know, that was a wavelength. We will launch on a dedicated Ariane 6.4 if it's available, then go once around the sun for about 400 days, a little further out than the Earth's distance, and that means when it crosses the Earth orbit again, it's about 50 million kilometers behind the Earth. And then we stop it there and start taking data. In June 2017, ESA selected this as L3, and now we're in the middle of the process of building it and making it work. And the clock is running. Only 15 years till launch, so we better not lose any time. I want to talk a little bit about science at the end, because after all, this is about science. LISA will be operating shortly after 2030. What will science be like at that time? Will we still need it? Do we have any clue what the big science questions are? There are so many wonderful telescopes that will be out there on the ground. We will have the LHC. Yes, I know, it's a particle accelerator, but it addresses many of the questions that LISA will be looking at. We will have the Large Synoptic Survey Telescope. We will have the beautiful optical telescopes, the large telescope, the very large telescope, the extremely large telescope, and the overwhelmingly large telescope. We'll all be observing. The Square Kilometer Array will be there, ALMA, the Event Horizon Telescope. In space, even the James Webb Space Telescope may have left the Earth by then. And there will be others, maybe even WFIRST will be flying, and we will have ground-based observatories. Yet, I dare to say that I can predict what the big science questions will be, that we will still be looking at in 2030. We will still be looking at cosmic structure formation. We will still not know how the black holes grew. We will be dealing with physics beyond the Higgs particle, supersymmetry, extra dimensions, phase transitions in the early universe, cosmic strings, and we will still not know what dark matter and dark energy is. All of these questions will be addressed by LISA, and I will not go through this list. I just show it to impress you a little bit. I only want to talk about one or two things. The first one is black holes, because they are close to my heart. This is the parameter space of black holes as it will be known by 2030. On the horizontal axis, you see the mass, 100, 1,000, a million, a billion solar masses. On the other axis, you see the distance, plotted as redshift. 0 is here and now in this lecture hall, that's down there. The farthest known cosmic objects ever observed are there at redshifts of 7 to 8. Beyond 10, the dark ages begin. That's the epoch of reionization. Dark ages because we will never see anything from there with light. That's why they're called dark ages. Now, what will these beautiful ground-based and optical instruments be looking at? This part here. The high end of the mass range, roughly out to reionization, will be observable by these wonderful telescopes. The gravitational wave detectors and the advanced form, advanced LIGO, advanced Virgo, will be looking at that part down there, the low end of the mass range, out to maybe redshifts of 2. But most of the parameter space, ET will look a little bit further out to a little higher masses, but the most part of the parameter range of black holes will be utterly unobserved by that time. And now you can guess, where will LISA be sensitive in this diagram? Where might it be? Sure. Right there. It'll cover the complete parameter space of black holes that remains out to arbitrary redshifts. To the beginning of the universe, if there was anything there, we have no clue, but if it was, we'll detect it. And we'll detect it with huge signal-to-noise ratio. I've plotted here a weak signal. That's a merger of two black holes of 100,000 solar masses at a redshift of 5. That's at the edge of the known universe. And that's the real signal, and it's plotted over the real noise, which is not speculation, because Pathfinder has measured it. In red is the instrumental noise, and if you say, oh, but there's no noise, it's a straight line. Not quite, it's almost a straight line. There's a tiny little bit of noise in there. And we are not guessing this, we've measured it. The good thing is that all binary black holes have to cross the LISA band at some point during their evolution. Here we see a few hypothetical evolutionary tracks of black hole growth So here, for example, you see the black hole we have in the center of our galaxy, about 4 million solar masses. So it has grown from unknown seeds back here and then grown up to here. Here is your typical QSO at redshifts of a few with billion solar masses, and other examples. We can observe the endpoint of the black hole development, but we have no idea where they came from. From here, from there, what was the instance? Was it light seeds, stellar collapse? LISA will see all of this. Another thing that people don't realize is LISA will be sensitive to dark matter if it forms a spike around the black hole. Because if something then falls into the black hole, the dark matter around it will change the phase of the in-spiral very sensitively. And the best thing is we are sensitive to dark matter even if it interacts only gravitationally. Because after all, it's gravity that we use to detect dark matter. We can also do cosmology with LISA. Cosmology with standard sirens, because coalescing compact black holes are standard sirens in the sense that by looking at their signal shape, you can tell the absolute luminosity. And then you compare the absolute luminosity with the apparent luminosity that you detect here, and just via 1 over r squared, you can calculate the distance. With these measurements, we can, within a few months, measure the Hubble constant to fractions of a percent. And within about a year, we can measure the dark energy equation of state parameter of dark energy to a few percent, which compares very favorably with dedicated missions that do nothing else than this, and we do it from first principles. As a matter of fact, we can do cosmology and measure the redshift to luminosity distance relation over a wide range, from distances in our immediate neighborhood all the way out to hundreds of gigaparsecs away. Of course, you need to analyze the data, and there our data analysts are currently busy practicing this on synthetic data sets. We better hurry up, because if the first data is only 15 years away, that's only 3 generations of graduate students. You can't do all that much with 3 generations, so you better practice. This is our best set so far, which contains 26.1 million galactic binaries. I don't know why 0.1, but something magic about it. Extreme mass ratio in spirals, a few massive black hole binaries, instrumental noise, and this is what it will sound like when LISA takes data. Listen, there's a merger coming. You're all experts now in data analysis, so. And the last thing now about LISA, the 2 LIGO black holes, we could have predicted them 10 years in advance. Here's the sensitivity curve of LIGO on the right, and you see the black curve there. Those are the LIGO black holes that we started out with about an hour ago, 50 minutes ago. They entered the sensitivity band at 30 hertz and then left at 250. But 10 years ago, here, 10 years, they were far apart, circling each other very slowly. They were in the middle of the LISA band, and not only could we have detected them, we could have predicted the time of merger to a second and the direction on the sky to better than a square degree. And I guarantee you that during that second, every big piece of glass on this planet would have looked in that direction to see whether there wouldn't be a little bit of a trace of an electromagnetic signal. Now, where are we? The call for mission concepts came in 2016. Decision on the implementation will come in the early 20s. Then the first large launch was originally scheduled in 28, the next one in 34. Unnecessary to mention that we are ready for an early launch. And if you still think this is too far away for you, then I have good news. If you want to see LISA technology and LISA interferometry in action earlier, you don't have to go far. You can stay near the Earth. A lot of what we know about the gravitational field of the Earth has been brought to us by the GRACE mission, which uses satellite-to-satellite tracking with microwaves. So there's the pair of satellites in the low Earth orbit coming, and if there's a mountain, then the mountain will first accelerate one of the satellites, then slow it down, then accelerate the other one, and then slow it down again. And that means the distance change between the two satellites encodes the mass distribution on the surface of the Earth. GRACE did this with microwaves, and GRACE was a very successful mission. Why is that important? Because of groundwater. Groundwater is important, but you can't see it. You could drill wells every couple hundred meters to see where the groundwater is, but it's a bit impractical to do this over the whole Earth. Groundwater is also not visible to remote sensing missions. You don't see it from the surface. But groundwater is heavy. And heavy water changes the gravitational field above the surface. And that means by measuring gravity with such a mission, you can detect the groundwater spatially and temporally resolved on the Earth. Why is this important? Because water is life. Water will be one of the most important geopolitical resources on this planet in the coming decades. GRACE was successful. We can, for example, tell that the Greenland ice is not just compactifying and sinking down, as you can tell from the surface. No, we know the mass is decreasing, but the resolution is not good enough to tell where it is disappearing and where it is going to. But that will change. It will change with GRACE follow-on, because the GRACE mission was such a big success. We are now looking at a new mission which uses quantum technology to get the next level of precision, and GRACE follow-on is carrying our laser interferometry, which is a direct application of laser interferometry for gravitational waves used for the humankind's benefit here on Earth. GRACE follow-on was launched on May 22nd from Vandenberg Air Force Base on a Falcon 9.
GRACE follow-on, continuing the legacy of the GRACE mission of tracking the movement of water across our planet.
A wonderful launch into a beautiful California blue sky out there. GRACE follow-on is operating as we speak, and the laser interferometer on board locked into operational state on the first try, autonomously, without human intervention from the ground. Just flying in the radio dark zone, it came back out, everything science mode on. And here's the first signal, the equivalent to first light on a telescope. So what you see down there is the ground track over the Himalaya. Yeah, see, there's the height profile of the Himalaya. And in red, you see the first laser interferometry curve. It's the change in inter-spacecraft distance in micrometers is measured by the laser interferometer. Okay, I know. Some of you say, well, I can see the Himalaya without a laser interferometer. Yes, that's true. It's the first light. So we're working on it. So you will see this improve. We will measure the water distribution to millimeters on the ground from up there. And finally, then we launch LISA, and we better do not lose any time with it, because I will hear the Big Bang with gravitational waves while I'm still alive, and so will you. Thank you. Thank you. You were a fantastic audience.
Do we have time for some questions? If there's a microphone, or if you have this Slido questions. So.
I think we had collected a few questions.
Yes.
Let me see. Anonymous. Oh, Anonymous has two questions here. What are some of the remaining engineering challenges left to solve to ensure LISA works with sufficient accuracy? Well, there are not that many left. It's mostly delta developments, because almost all technology that we needed for LISA we had on LISA Pathfinder. And we've also been able to extend the LISA Pathfinder measurements down to very low frequencies, which was a surprise. We could go to 20 microhertz, which is such a pain in the neck to measure anything at 10⁻⁴ hertz. I'll give you an example of what that means. 10⁻⁴ hertz means one oscillation is 10,000 seconds. That's 3 hours. So it means you need a few oscillations to see something. That's about 30 hours. And then you have to average down the power spectrum that you're recording, which takes a few averages. So 30 hours is a day. Let's say 8 averages times a day. So 1.5 weeks for one data point. And then you vary a parameter and do something. So, but anyway, the telescope needs some more work, but that's underway. There's some more work required on the high power laser, but we don't expect any surprises there. Sound, straightforward engineering work will do it. So I think we don't have to expect any skeleton in the closet. Is there a specific reason for an Earth lagging, Lisa? No, it could be Earth leading, Earth lagging. It's little details in the mission launch scenario. It's the time of the year when you launch. There's nothing magic about it. We're still optimizing it. The expected lifetime will be supplies limited. Currently, we're assuming that we operate with cold gas propulsion when we're on orbit to hold the thing steady against the solar radiation pressure, which is the single largest disturbance force, because it tends to wiggle the satellite and push it away. So, but that only requires micronewton. Unfortunately, cold gas is kind of the steam engine of propulsion. It's big, bulky, boring, but it works. That's the advantage. And we cannot carry tons of cold gas with us. And so for a 10-year mission, a few hundred kilograms of nitrogen is about all you can carry. So that will limit the lifetime of the mission. Why do we see a lag between gravitational whirlwind and gamma ray burst? That's a very intelligent question. The details of the process is not completely clear, but these are different. The basic idea is simple. We see different physical processes. The gravitational wave immediately gets excited when the two things crash into each other, because it's the mass that moves quickly that generates the gravitational waves. When they do this, then they heat up. And that takes a moment before they heat up. And then the gamma ray burst comes out. And then we see a whole host of other processes as the big fireball that is then created cools down and also gets reheated by a nuclear decay chain, because what is created here is many, many heavy elements that are way too neutron rich. And so they drip down because they have way too many neutrons, and this fuels energy into the thing again. And then finally, after about 2 weeks, the whole thing is completely transparent and so cool that you start beginning to see the radio waves. So it's a fantastic laboratory. It's the first time ever we can watch in real time how a cosmic fireball develops in there. Extreme accuracies of LISA, how we will be able to, or you can read the same thing, yeah? Distinguish awesome amounts of actual signals out there from random noise. Well, easy, I can tell you. How? With great care. No, it's actually with sound data analysis technology. First of all, the instrumental noise will not even be visible in LISA. LISA at all frequencies is limited by signal. So it's an orthogonal data analysis problem to the data analysis problem you have on the ground. On the ground, you detect noise all the time. And once in a while, you have to dig a little bit of signal out of the noise. On LISA, you're detecting signal all the time. And it is only the intelligence of your data analysis routine that lets you dig into the signal. First, you identify the big ones. They will stand out with signal-to-noise ratios of thousands. Unheard of. So they're identified, you model them, you take them out. And then you keep going, until you reach a non-reducible signal background. That is currently being practiced. I gave you an example of the whole enchilada, that's what it was called. 26 million galactic binaries, and the best data analysts get about 20 to 30,000 out of these. The rest then forms a background. But that gets better and better as the mission goes on, because your frequency resolution increases. Frequency resolution is 1/mission lifetime. And so as the mission goes on, you can dig deeper and deeper into the signal background in there. Why was your talk so awesome? Because I love you. It's easy. I have my fun talking to you. What social impact of hearing the Big Bang you would like to see? The biggest social impact, I think, is to create enthusiasm for science and engineering out there, because this is something that appeals immediately to people. So I know how it feels to be on the sidelines, to be an exotic. We were always invited to conferences as the entertainment to give a talk. Now we have a few signals, and suddenly people pay attention, and we are mainstream astronomers. The whole life is different now. So, what do you expect the Big Bang to sound like? Well, maybe like that. I have no clue. Nobody has a clue. This is total discovery space. I always say we have many, many theories about the early universe. So it was probably not boring at all what has happened in the early universe. But we have too many of those. We have more theories than we have theorists about the early universe. The good thing is, all these theories predict a certain type of gravitational wave signal that must have been created. It will be the experiment that decides in the end. And also, when I say the Big Bang, let's be clear here. None of our theories reaches the Big Bang right now. We can get very close to the Big Bang. But the Big Bang itself, if it ever existed, is not contained, not described by any of our physical theories. We cannot reach it. So, the experiment is the only way to find out, and gravitational waves are the only way to get close to the Big Bang, because the universe was opaque, not transparent for the first 380,000 years. That will forever be hidden from our view. Gravitational waves are the only hope. Any features in the current LIGO that cannot yet be explained? Well, there are so many noise features. Not all noise features are completely understood. But if you mean signal features, let me say stay tuned. The result of the data analysis will appear in the open literature. And also with the beginning of data taking, 03, that's the next data taking run, probably next spring, the data will be public. So if you go on the website, you can download the analysis tools, you can analyze the data yourself, if you like, and see what's happening. So it will be a whole new ballpark, the era of open science in advanced LIGO. And for the other signals, they're still being analyzed, and publications are coming out soon. So we've sat on the first event for 5 months. 1,000 people knew about it, and nobody talked. And the journalists kept pestering me when the first rumors came out. Then I always told them, guys and girls, we've been waiting for 100 years for this signal. Really, a few more weeks don't make a difference. Why can't you just wait till we know what we are doing, until we understand what we are doing, and then we talk about it, but not before, which might be good in general anyway.
Okay, Thank you very much.
Thank you.